Hi. In this video, we're going to be looking at how you can use the Python programming language to understand some basic thermodynamics. By understand, I mean we're going to be simulating basic thermodynamics and then seeing what happens when we change various things. We can get a deeper understanding of what's actually happening. Now, if we go to the Wikipedia page, or temperature, for example, it tells us that the temperature of a system is related directly proportional to the average kinetic energy of the particles. So what does this mean? It means, for example, if you had gas atoms in a box and the gas atoms were free to collide with each other and the walls of the system, then the value that we would call temperature is really just related to the average kinetic energy of each particle. So as we look at this GIF here on Wikipedia, we can see that if you follow just one of the particles, so try and keep track of one of the red particles, you'll see that as it bounces around and collides off the walls and other particles, its speed changes. Right, you can see some of them, sometimes it's moving very slowly, sometimes it's moving very fast, other times it's moving somewhere in between. And this is basically saying that if we counted the kinetic energy, we summed up the kinetic energy of all those particles, then that would, and then calculated the average, that would be directly proportional to its temperature, or the thing we call temperature is related to the average kinetic energy of all of those particles. If we go one step further, we can get the distribution of speeds for the particles in the system. So if you had a large number of particles in a closed system, and then we took each of those particles and measured its speed, we would get a distribution like this. So for example, the helium atom is very light. We would get a distribution in which most of the helium atoms are moving with a speed around 1,200 meters per second. But there are occasions where some of the atoms might be moving very slowly and some of the atoms might be moving very fast. We then go to a much heavier atom, say xenon. For the same temperature, we see that on average, the xenon atoms are moving slower than the helium atoms would because they're much more massive. It's very unlikely that they would be able to attain much higher speeds. So we're going to go ahead and simulate this system. Then we're going to try and get an understanding of why these distributions appear. Can we make these distributions from just some very simple physics laws, such as elastic collisions? So when I was an undergraduate student studying physics, we would do things like this in the C programming language. And then we would have to export the data to a file and then use some other software, such as NuPlot, to actually be able to plot the simulation and to actually see what's happening. These days, most undergraduates will be learning Python as part of their degree, and Python's a very powerful programming language, especially for things like this, particularly in data science. It has all the tools necessary to be able to do these simulations and visualize them. So this tutorial, this video will be focused on using Python to actually do this, and you'll find it's actually quite simple. So the first thing we're going to do is we're going to load up Spider. So Spider is a IDE that comes packaged with the Anaconda Python libraries. Is probably the one that you'll be downloading as an undergraduate student. So let's go ahead and start coding. So the first thing we're going to do is we're going to import NumPy. NumPy is a numerical library, stands for numerical Python. It will allow us to do certain things with vectors and matrices. The second thing we're going to want to do is we want to be able to see simulation itself. So we want visual confirmation that it's working. We're going to go ahead and import matplotlib, which is a plotting library. And the first thing we're going to do now is we're going to think, so we need some way of representing a particle. So what is a particle? A particle in the loosest sense is just an object. If you use object-oriented programming, we can create an object that represents a particle and then think about what properties a particle has. If we go ahead and create a class called particle, and then what happens is when the particle is created, so when this class is initialized, it calls this function. And we need to now think, what do we need to represent the particle? Well, we know the particle needs a position in space. So we can go ahead and call that R. So R, the position vector, typically holds the X and Y coordinate, and Z if we're doing this in 3D. And we're going to give it a default value of 0. Using NumPy, this creates an array with 0, 0 as the two elements. Also going to need speed, because a particle can't move unless it has speed. And again, we'll initialize that to 0. So the default state of a particle is to be at position 0, 0 with no speed. Also, a particle needs a radius, so in order for two particles to collide, especially if they're hard collisions or hard elastic spheres, they will need a radius. That's something small. We're also going to need a mass at 1, because when two particles collide off each other, the mass determines their relative speeds and momentums after collision. And just to be fun, we're going to give them a colour. By default, the colour will be blue. We can go ahead and highlight certain particles by changing the colour to red. In this particular simulation as well, we're going to give the particles an ID. And why give the particles an ID? It will allow us to track individual particles. It will be a way in which we can actually identify a particle over time. So when the particle is created, this function here is called, so the initializer method is called, and we won't be able to use this R, V, R, M and color variable unless we assign that variable to the class itself. So to do that, you write self.id equals ID. So whatever we pass to the class upon initialization, this ID variable is stored in the class itself as another variable called ID. Because it's Python, we can go ahead and make this a bit neater. So we can do something called tuple assignment. So we can write all of the variables. I'm giving them the same name stored in the class. I'm going to go ahead and say what that does when a particle is created, it has all these default values and then they're stored in that particle class itself, so the instance of that class. First thing we need to do. The next thing we need to think of is where are these particles going to be? So these particles are going to be in a box, and this box itself is a system that evolves in time. So we can think of the system as another class. We can call it a sim. It's a simulation. And we'll give it some very basic initialization code. So it's going to have a time increment. So how much time passes between each iteration of the simulation. And we're also going to give it a number of particles. Let's say something simple like 10. When this class is created, it will be created with two internal variables called dt and mp, and they will be assigned default values of 10 microseconds and 10 particles, respectively. And then we need to go ahead and create the particles. So what we'll do here is we'll create a list, and we'll use a list comprehension to create the particles themselves. What this bit of code will do here is it will create a list of 10 particles, and it will send a value of I, which goes from 0 to 10 in steps of 1, 0 to 9 in steps of 1. And so when it calls this particle constructor, it will be setting the ID to I. So we'll have 10 particles, each with an ID of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's our basic setup. So we've got a way of representing a particle and a simulation to contain the particle. And so as an undergraduate just learning Python, you're probably not going to be familiar with debugging. And personally for me, I find the best way to see if something's working is to actually visually see it. So we're going to just go ahead and plot these particles. And then as we go through the code, implementing new features, such as moving the particles about, having the particles collide. We'll be constantly checking visually to see if that's working. So the easiest way to take this, to create a plot. So if we go ahead and run this code now, it's created a plot, but we haven't actually plotted anything yet. And now we need to go ahead and create a scatter plot. So the syntax will be x.scatter. And what x.scatter needs is a x and y values in lists or arrays. So we need some way of getting the x and y values from the simulation class. So we're going to define a function. And in order to save time, I'll just copy over some code. What this code will do here is it will loop over all the particles in this list of particles, which is defined in the simulation, and then it will return a list of the position vectors in XY format. So if I go ahead and create an instance of the simulation class, and then we try and run this, what we'll see is it won't work. And that's because when we look at what this returns, so quickly go ahead and do something like this. We can use the variable explorer that's built into Spider. We'd look at what this variable a is called. It is a list numpy arrays. It's a list of x, y pairs, but the x.scatter requires a list of x and then a list of y. So the easiest way we can do this is to look again what our variable a is. The return value from the particle positions. You see it's a list of two vectors. Now if you go ahead and do numpy.array on this, then look at the shape, what we see is it now puts it into a matrix. It's 10 rows by 2 columns. What we can go ahead and do now, the x.scatter, we can say, take our vector, our matrix containing all our positions. Remember, this is now a 10 by 2 matrix in which the first column is the x positions and the second column is the y positions. So we can then just column index this. We get the first column for the x, second column for the y. Go ahead and run that, and we see there. So this is all 10 of our particles at position 0, 0, stacked on top of each other. But that's not very interesting. So we need a way of distributing the particles in space. Let's go ahead and create a way to do that. Well, label these, so this can be our plot codes. So the first thing we're going to want to do is we're going to want to access each particle from the simulation and then give it a position. So to do that in Python, we can do for particle in sim.particles. This means each iteration of the loop will return a particle that's contained within the sim. We can then do particle.r equal to numpy.array. Do something better here. We can do numpy.random uniform. This gives you a uniformly distributed random number between low and high. So let's say between -1, 1. And then the size equals 2. Always make sure you spell your variables correctly. Go ahead and see. So it's distributed our 10 particles within the box bounded by -1, 1. Yeah, this is really good. It seems to be working. In order to make this a bit more neat, we're not going to be putting in -1 and 1 all the time when we're trying to determine where the particles are. Really, that's going to be held by the simulation itself. So the simulation is basically defining this box and defining how the particles within the box move over time. So we can give it a variable, a class-wide variable called x and y. So this is the size of the box in the x and the y direction. And then in our code here, we can go ahead and do something like this. A bit x over 2. And this works with square boxes, but in case x and y were different, we need some way of making this different, which we can do. And doing this is quite simple. All we need to do is, instead of giving it a single value for the low and a single value for the high, we give it 2 values. Y over 2. Same for this side. Sim.y over 2. Go ahead and run that. It looks like nothing's changed. But if we go ahead and change, say, x to 10, we can see that we get values that are uniformly distributed between -5 and 5 on the x-axis and -1 and 1 on the y-axis. Works. Go ahead and change this back to 2, however. Next thing we're going to want to do is to come up with some way of being able to increment the particle's position based on its speed. The simplest way to do this would be to go into the simulation class, because we already have a variable called dt, which represents a time delta, so a difference in time, or a time step. We can implement the Euler method. What's the Euler method? If we create a function called increment, which increments the time of the simulation, so it increments the simulation by 1 delta t time, we can go ahead and say that for each particle from the list of particles, we can say particle.r, so its position vector in space, plus equals the time step, so delta time times the speed of that particle. It's basically saying, in this small unit of time, move the particle by the small unit of time times its speed, because obviously speed times time has a unit of distance, and it tells you the incremental change in distance with regards to its instantaneous speed. And that's a way for us to increment our simulation over time. And so let's go ahead and plot this. Of course, some of the eagle-eyed viewers may realize that this won't work. So if I call the method sim.increment, plot it on the same plot, we should see orange dots appear. But unfortunately, they're appearing on the blue dots because the blue dots do not have any speed. So the particles have no speed associated with them. So we need to give the particles some speed in order for them to be able to evolve over time. So let's go ahead and figure out a way to add some particle speed. And what we could do is just give all the particles single speed in a particular direction. Remember, this is just visually checking whether this is working. Particle dot v, which is the speed, and then we'll give it a speed of 1, and we'll give it an angle of 45 degrees. Each particle now has a speed with magnitude 1 orientated at a 45-degree angle. During one time step of 10 microseconds, we should see a small movement. Not appearing on here. Let's change the time step to, say, 1/100th of a second. And there we can see all the particles have shifted at 45 degrees from their original position during one time step. So this is working. Now, because this is a simulation that's happening over time, we'd like a way of actually animating this seeing what happens over time. So matplotlib has a really nice function called func animation. So function animation. We go ahead and import this. Will give us access function allows us to animate a plot over time. I'm just going to move that down there because we're getting rid of that soon. So the first thing we do, we create an empty plot. So we create a scatter plot of our particles, but don't actually plot anything. But what this does return, it returns a collection of objects, which is the little circles, which will be representing the particles. We'll go ahead, do that. Then we need to call the function animation. So let's go ahead and write that. And we see that it needs a few variables. It needs a figure, which we've completely called fig. It needs a function to call. So this is the function that's called every time it wants to update. We'll go ahead and create a function called update. It accepts one argument called the frame, which we'll see later. And it returns a single object that needs updating. So every time we go through this animation, we're going to want to update the positions of the scatter plot. We'll update. The frames, we're going to give it a range of 1200, so it's going to be plotting 1200 frames. Also needs something called an initiation function. We'll define here. So this is the function that is first called before the frames begin to update. We're going to enable blitzing. So blitzing means that only change the parts of the plot that have actually changed. Don't draw the entire plot again. Just overwrite the bits that have changed. And this is a lot faster. So a lot of people might be watching this video and saying, why are you using matplotlib? It's quite a slow library. There's much better Python libraries to actually be plotting and creating animated plots. My answer to that would be that when you first start learning Python, you're likely to encounter matplotlib as the first plotting library that you'll be using. So I think it's fair to use that as the plotting library. Give an interval, so this is the amount of seconds that each frame stays on before being animated. So think of it as the inverse of the frame rate. If you wanted 30 frames a second, the interval would be 1/30th of a second. You can also give it a repeat equals false. This says that once the 1200 frames have been drawn, don't continue, don't loop the animation. Okay, go ahead and run that, check if it works. Doesn't, because I spelled interval wrong. And that is working, but you see it's not actually updating because we're not doing anything to the plot. What we can do here is in the update function, we're going to update our simulation. So sim.increment. Go ahead and plot that. It's still not working, and that's because although we've incremented the simulation so the particle positions are changing, we've not actually changed the position of the scatter plots. So in order to do that, we need to call a function called offsets. Again, we're going to use our 2D array from the sim particles positions. Get rid of this. And we can see the problem we're having is when we launch this, it's probably working, but the plot axes aren't right. So let's use default plot axes of minus 0.05 to 0.05, which is wrong because we know our simulation goes from -1 to 1 on both axes. And that is solved by going into the initialization function. The first thing plot needs to do is to set the axes correctly before beginning to update. If we go ahead and run that, we can see that it's working. So the particles are moving at their given speed, which was a magnitude of 1 at 45-degree angle, and then they move off. I think that's where we'll leave this video. In the next video, we'll go ahead and create some collision detection on the walls and between the particles themselves. And we'll be able to try and see the particles bouncing around in the simulation. So stay tuned.